This is lesson 1.5 in data management. It's the last lesson in the first unit, and this unit's been about some things we need to know for probability, and this is also a main concept to do with probability. Independent and dependent events. When multiple events occur in a probability experiment, they're called compound events. So two or more things happening, one after another, usually compound events, such as pulling a card from a deck and then rolling a die or something like that, two different things, but you're putting them together. Sometimes the probability of one event depends on whether another event occurs. Sometimes it doesn't. When one event has no effect on the probability of another, then the events are called independent. So independent events, we like those, at least as far as doing probability goes, because they're easy. We can find the probability of each part of the compound event individually and then combine them. Here's an example. Olivia has 4 highlighter pens. In her pencil case, 2 are yellow, 1 is green, 1 is orange. Okay. She reaches into the pencil case randomly, chooses a highlighter. After she uses it, she immediately replaces it. That's key in the case, so it can be used again. What's the probability that she'll choose 2 yellow highlighters in a row? All right, so I'm going to draw a tree diagram over here. So she reaches in the first time, and there's 4 different things that she might pull out. A yellow, a green, or an orange highlighter. If she pulls out, and there's two different yellow highlighters, so I put a different path for each. But if she pulls out the first yellow highlighter, or the green one, or the orange one, or whatever, the second yellow one, she's going to put it back in. So no matter what she picks the first time, she's going to still have 4 to choose from. Still have the 2 yellows, the green and the orange. Now, as you can see, tree diagrams get a bit messy fairly quickly. So I'll do my best to keep it tidy, but there you go. So it doesn't matter what she drew the first time. She has 4 choices, the same 4 choices for the second. We've seen before that if we do a simple tree diagram like this one, then we can count up the number of paths for our sample space, N of S. So the total number of outcomes is the total number of paths, and if you count them, you'll see that there's 16 paths. Now, if event A is getting 2 yellows, then we just have to find all the paths where that happens. So here's one path where you get 2 yellows. Here's another path where you get 2 yellows. How can I show this? It's going to start to get messy, isn't it? Here's another one with 2 yellows. Here's another one here with 2 yellows, and here's another one here with 2 yellows. So there's those 4 paths where there's 2 yellows. So N of A is 4. So the probability of A, as we've already seen theoretically, is N of A over N of S. So it's going to be 4 over, I'm going to actually write the formula out again. We haven't talked about it for a bit. N of S over N of A over N of S. One more time. N of A over N of S. So it's 4 over 16, and of course we reduce it, so we got 1 over 4. So the probability of getting 2 yellows in a row is 1 in 4. The probability of getting a yellow highlighter followed by a blue highlighter, let's highlight that in blue. So yellow followed by blue. Oh, wait a second. What's the probability of getting a blue? There are no blue, are there? Well, in that case, in that case, what we have is 0 paths. 0 over 16 means that there's a 0% probability of getting yellow followed by blue, which makes perfect sense, right? No blue highlighters makes it impossible. There's another principle that we can use instead of having to draw a tree diagram, though. It's called the multiplicative principle, the fundamental counting principle for independent events. So this is another formula that you're going to need to know. And it says that the probability of two independent events is the individual probabilities multiplied together. So the probability of A and B happening is the probability of A times the probability of B. Verify the answers to example 1 using the multiplicative principle. Sure. All right, well, the probability of getting a yellow on any one draw, I guess let's just zoom in here. There's 2 yellows. So let's just say P of Y for probability of yellow. There's 2 yellows, and there's 4 highlighters altogether, right? So for one draw, you've got a 2 out of 4 chance of pulling out a yellow highlighter. So that reduces to 1/2. The probability of getting a blue highlighter, as we've already seen, there's 0 blues out of the 4 in there. So the probability on any single draw of getting blue is 0. So this multiplicative principle, first let's do probability of yellow and yellow, would be the probability of yellow times the probability of yellow. We already saw that probability of yellow is 1/2. So 1/2 times 1/2 equals 1/4. That matches what I had for part A above. Probability of yellow followed by blue would be the probability of yellow times the probability of blue, which is 1/2 again for the yellow times 0 for the blue, which would give us 0 overall. And again, that also matches part B from above. So that does confirm what we already found out using the tree diagram. So that's the multiplicative principle, or otherwise known as the fundamental counting principle for independent events. What's the probability of rolling a standard die and drawing a card from a deck and getting an ace, a 4, and an ace? All right. Well, the probability of, let's say that event A is getting the 4, and event B is getting an ace drawn from a deck. So the probability of A is, there's 1 4 out of 6 sides on a die, so it's 1/6. The probability of B, drawing an ace, is there's 4 aces out of 52 cards in a deck, which reduces to 1/13. So the probability of A and B getting a 4 and an ace in this compound event is the probability of A times the probability of B. So 1/6 times 1/13, which equals 1/78. So it's a powerful concept that we can find the overall probability of multiple events happening, multiple things happening, compound events in other words, simply by multiplying those individual probabilities together. However, they have to be independent in order for that to work. When one event has an effect on the probability of another, the events are called dependent events. So independent means that one event doesn't affect the other one. As soon as one does affect the other, now we've got dependent events. And we can still calculate probabilities for them, but we just need to be aware that we're dealing with dependent events so we can take appropriate steps. The multiplicative principle for dependent events says that the probability of 2 dependent events, A and B, occurring where the probability of B depends on the probability of A, and I think that should say where the probability of B depends on the probability of A, is probability of A and B equals the probability of A times the probability of B given A. So that's the conditional probability, or that's something called conditional probability. P slash A is conditional probability. So we can just work on it. Sorry, let's write this out. So we can just write that out. And again, just have to know what that means. So a study of a telemarketing company's data shows that 2,000 calls placed. The experimental probability of a call receiver staying on the line for at least a minute was 16%. So let's just say staying on the line for at least a minute was event A. That means that P of A equals 0.16. The conditional probability of a sale resulting, so that's B given A, is probability. So probability of B given A, that's not an I, that's a slash, is 0.1. And no sale was made if a receiver did not stay on the line for at least a minute. So probability of A and B in this case is going to be the probability of A times the probability of B given A since they have to stay on the line for at least a minute before a sale can happen. So it's going to be 0.16 times 0.1. So the probability is 0.016. And then we can calculate the number of sales by doing the 2,000 calls times the probability of making a sale on any one call. That's going to give us our prediction. So we'd expect 32 sales in this example. Last example, just quickly run through it. A roulette wheel uses 38 spaces, has 38 spaces. 18 are red, 18 are black, 2 are green. What's the probability of landing on a black number twice in a row? Okay, so the probability of getting black, I'll just use B for event black, is 18 over 38, which reduces to 9 over 19. Probability of red, likewise, is 18 red over the 38, so that's 9 over 19 as well. Probability of getting black twice then, so probability of B and B is going to be 9 over 19 times 9 over 19, which equals 81 over 361. And then getting black, then red, is also going to be 9 over 19 times 9 over 19. We're going to get the exact same results in this case for this particular one. And that's it for this lesson.